So welcome everybody to the 10th lecture of Digital Communication course. This is the second part of this lecture. It's named Correlative Level Coding or Due Binary Signaling. In the previous lecture, we talked about it briefly and we discussed what's correlative level coding. It's basically introducing artificial intersymbol interference to your data stream so that you can double your transmission capacity. In that case, you will be able to transmit data rate of 2W within a bandwidth equals to W. And we gave an example and we followed the stream, how it changes after each block. And also we studied its frequency response, its impulse response by drawing and by mathematical formulas. And also we talked briefly about the shortcomings of this scheme, the drawbacks, the demerits, the disadvantages of due binary signaling. We said the first one is error propagation. When you make an error in one of the bits, it affects the other coming consecutive bits after it. And also it has DC value at zero frequency. We have seen this from the frequency response of the due binary signaling system that there is DC value. What DC means, at frequency equals zero, you have a response. And today we want to come up with methods and techniques that can avoid these drawbacks, these shortcomings. So basically, in order to overcome error propagation problem, we are going to use precoding techniques. Before we enter it and start using the due binary signaling, we will use precoding. What's precoding in this case? Precoding is basically an XOR operation between the data bits before I use pulse amplitude modulation. So basically, the new data bits stream that you have, it will be equal to the original data stream XORed with the previous bits of the output data bit stream. We will explain this and you will understand it very deeply by giving an example later on. This XOR operation, this is basically XOR operation. And everybody knows XOR operation. If you have 0, 1, the result is 1. If you have 1, 0, the result also 1. If you have 0, 0, the result is 0. If you have 1, 1, the result is 0. So basically you get 1 when one of them is different. When both are similar, 0. So this is basically what you do to your data stream. And what's the new structure of the due binary signaling? It's given in this slide. As you can see, this is the same pulse amplitude modulator, due binary coder is the same, sampler is the same, output, but here only the difference is here at the input. Here this is the XOR operation. The XOR operation is represented by this section. You have your input binary sequence PK, and this is modular to addition. It's XOR operation basically, and you take here your output data stream and delay it by TB, and then you XOR it with the input binary sequence to get the new sequence. We call the new sequence here precoded data bit sequence, and by doing so we can avoid the error propagation problem. So let's have an example, and so that we can understand it in a much better way. And we start by agreeing on the fact that the coded sequence CK produced with precoding consists of 3 levels as illustrated. We all know that CK, the due binary signaling basically, which is here CK, at the output here. It's basically, we know that you take the pulse, the current pulse, you add it to the current consecutive pulse, just the previous one, to get a new value. And due to this superposition property, we call it artificial intersymbol interference, because they are overlapping on top of each other, as if you have this signal and another signal, you add it on top of it. This is full overlap interference. So the result at the end of the day is 0 if data symbol is 1, and it's plus or minus 2 if data symbol is 0. So basically, just you can check this by giving different values for AK, and you will find out that CK can only take 0 or minus 2 or plus 2. So at the receiver side, when you want to detect, considering that you are using precoding, then the symbol PK, the detected one, will be considered as 1 if the magnitude of CK less than 1. However, if the magnitude of CK is greater than 1, then symbol PK is 0. How do you get the magnitude of CK? CK can be positive or negative. How to get only the positive? You use rectifier like diode. If you remember from electronics, you get only the positive. The negative becomes positive actually. Yes, you remember? And your whole signal becomes positive above 0. From this, the decoder can be simple rectifier followed by a decision device, and we call the decision device comparator. And this is low complexity receiver structure compared to coherent receivers. So basically, the block diagram at the receiver will be something like this. You have your CK, you pass it through rectifier, which is basically diode, and then you have the absolute value of CK after the diode, and then you put a threshold. This is optimal threshold, and the threshold in this case should be 1, not 0, 1. And then you compare with this threshold. If the amplitude of CK is less than 1, then PK, the data bit you transmitted, is 1. If it is greater than 1, then PK is equal to 0. So let's give an example. In the exam, you might get something similar to this. I just give you the binary sequence. The binary sequence, any data bit stream, of course, I can give. Not necessarily this, so that you don't memorize. You understand? Let's say the sequence is 0, 0, 1, 0, 1, 1, 0. And I tell you, encode this sequence using dual binary coding with precoding to avoid error propagation. And I might ask you, why do we use precoding? To avoid error propagation. You tell me, first I find DK, the precoded sequence. What's DK? DK is basically BK, yes? This value, BK, XORed with DK minus 1, which is this. So you take this value, XOR them with each other. 0 XORed with 1. What's the result? The result is here, 1. Then 0 XORed with 1. The result is 1. 1 with 1, 0. 0 with 0, 0. 1 with 0, 1. 1 with 1, 0. 0 with 0, 0. So you got DK. This is only the precoded sequence. Then I tell you this sequence passes through amplitude pulse modulator. What's the AK? You tell me if it is 1, then it becomes plus 1 or plus 5, plus 6, according to the question. And if it is 0, then it gives minus A, minus 1. This is simple. Then find CK, which is the signal after dual binary signaling. You tell me, I know that CK is equal to AK plus AK minus 1. True? So you just take this value, this is AK, and this is AK minus 1. You sum them. 1 plus 1 plus 2. 1 plus 1 plus 2. Minus 1 plus 1, 0. Minus 1 minus 1 minus 2. 1 plus minus 1, 0. Minus 1 plus 1, 0. Minus 1, minus 1, minus 2. It's easy, but if you make a single mistake, you are gone. The whole sequence will be wrong. So you must be very careful. Binary sequence obtained by applying decision rule. Now I tell you, decode this sequence. I might not bring the whole equation as you can see here. In multiple choice, I can give you this, for example, this sequence. I tell you this is CK. This is the output of two binary signaling, and assume we are using precoding. What was the transmitted sequence bits? You tell me the decision rule says that if the magnitude of CK is greater than 1, then what I transmitted is 0. If CK amplitude of CK was less than 1, then what I transmitted was 1. You apply this rule because in that case you use rectifier and then comparator. This is comparator actually when I say greater or less. And this is magnitude, absolute value is due to the rectifier. So in this case, plus 2, is it greater than 1 or less than 1? Greater, then what was the symbol, the data bit? 0. Plus 2, greater, 0. 0, 1, 1, less 1. And you continue like this. So this is basically these BK, DK, AK, CK are basically here in the block diagram here, shown here. I can trace them. BK, DK, AK, CK. This is the block diagram. These are the bits actually, the ones I was talking about. These are the sequences. Yes? This is what I tell you when I tell you check your code using MATLAB step by step. I mean here. After each step, there is each step is a block diagram, is a block. So you check after this step, what happened to my data, how it should be, what's it actually, why this error is happening. This is how you find. This is how we teach you how to debug errors. If you have error in your code, to trace it. You have theory in your mind, you see that this should be like this, the sequence should be, if it's not like this, then this means that I made some errors in the detection or clear. Then we solved the first problem, the error propagation. How did we solve the first problem, the error propagation? We solved it by using dual binary signaling. Good? Everybody with us? Okay, now the second problem. We said the second problem is you have DC value at frequency equal 0. What's the problem? You tell me it's a problem. I don't see it a problem. It's a problem because you cannot send DC values over wireless channels. Wireless channels, they are AC channels. They don't carry DC. So if you have, as long as you have DC value, you cannot send, you cannot use this scheme for wireless. So what's the solution? Modify your dual binary sequence, modify the pulse, or in such a way that the response of this pulse in the frequency domain has 0. How do we do that? We come up with a scheme called modified dual binary signaling. And in dual binary signaling, we know that the frequency response is non-zero at the origin. If you remember with me, the response was of dual binary signaling in the frequency domain was something like this. Yes? Here, it was not 0. This is the frequency and this is the amplitude of HF. Yes? And here at this point, this is 0 frequency. What's the amplitude? There is amplitude. This is the DC. This is what I mean by DC. I don't want this. I want this to be 0. We can correct this deficiency, this drawback, we can solve it by using the class for partial response. So we will use partial response signaling scheme to solve this problem. What's this partial response? It says that You remember this the first block here looks like XOR operation. It's basically, yes, XOR operation, but the delay here is 2 TB, not TB. So you know this. You have BK, you get DK. Still, we are in bit level domain. This BK is bit and DK and BK bits. Only the difference is XOR operation. We have DK minus 2. After that, you have pulse amplitude modulator that gives +1, -1 to the bits. And then here is the due binary, the new thing we are introducing. This is, we call it modified due binary conversion filter. And this basically what makes your response 0 in the frequency domain at frequency equals 0. So basically, it takes your pulse amplitude modulated sequence, AK, here from here, and delays it by 2 TB, 2 period of 4 bits, and then sum it with the current one. Then go to the ideal channel Nyquist filter, like rect or raised cosine or sinc, and then you sample at t equal k TB, TB by TB, and then you can find CK, which is the due binary signaling sequence, CK, the inter-symbol interference sequence. This is the block diagram. Now we understand the block diagram, but what's the mathematical formulas now? You say that this block diagram can make sure that the frequency response is 0 at frequency equals 0. But where is it? Can you show it to me in math and in diagrams? We can. Let's come. This is the frequency response of this filter. When you write these in math, you find that this is equal to H Nyquist. If I tell you write this in math, it's equal to H Nyquist in the frequency domain multiplied by 1 minus exponential e to minus j 4 by ftb. Anybody can tell me from where this exponential came? From the block diagram. How did I know that there is exponential from the block diagram? I want you to answer me. 1, in the formula here I see 1, and here I see exponential. From where 1 comes, this is what I need to know, and from where exponential comes. 1 comes from this line. You don't have any delay, direct. And the exponential comes from this delay, 2 TB. You delay by 2 TB. Delay in time equal to phase shift in frequency. Fourier transform from signal and system, yes? You know this. Delay in time equal to phase shift in frequency. So, and this, you just multiply it because both of them are coming to this. This is common factor. This is basically from where it came. Now you understand this equation, what's it, how it's derived? Yes, everybody can read it now. You must link it with the block diagram and be able to see that it came from the block diagram. And then you can simplify it more. What do you do to simplify more? Exponential, you take exponential minus j2 by ftb as common factor outside, which is this. And then you have here 1, and again, you end up getting here sine with multiplied by 2j and with the H Nyquist. This step in the exam, if I ask, for example, what's the H, the impulse frequency, the frequency response from the block diagram, you don't need to give me this. Just this is enough. Because this is coming from this. This is simplification. But I want to see that you are understanding it. If I tell you to simplify it, then you use the Euler identity. What's Euler identity? Again, remind you of it. If you have E minus Jx, then this is equal to cosine x, yes, plus j minus, because you have minus j sine x. This is the Euler identity that you can use to simplify your expression more. Easy, not difficult, from calculus test. Now, you got the functions, the formulas of the function in math. Can you draw them? You draw the amplitude of the frequency response. When you draw the amplitude of the frequency response, you, for example, put at frequency equals 0, you substitute here f0, here substitute 0, and calculate exponential of 0, e to power 0, what? 1. 1 minus 1, 0. Anything multiplied by 0, 0, then it's right. At 0, I will get frequency equal to 0. See? Then I don't have DC component. If I don't have DC component, the signal can go through wireless channel. I can send it through wireless. And this is the function that I use to draw this. If you just use it, you will end up getting this response. Of course, I can ask you, find the response, also prove that the response at frequency equal 1 over 2 TB is equal to 0. You substitute here 1 over 2 TB f equal to 1, and you see that this again gives you 0. I prove that the maximum is happening at 1 over 4 TB. You just substitute here and find it that it's really maximum too. You cannot get more than this. So the point, the most important thing, that you got 0 at the center, at the origin. And here, this is the phase shift. How do you find the phase shift? The tan inverse of the complex value over the imaginary value over the real. So here you have exponential, and you convert this to rect form. This is polar form. This is like the amplitude. This is the amplitude, yes? This part is the amplitude, and the part is, like when I tell you represent this complex number in polar form, what do? Suppose I gave you this number, 5 plus j6. Represent this in polar form. What do you need to do? And I say this is A. This is vector A, or complex number A. 5 plus 6j. I want this in a vector form. What's vector form? Means find the absolute value of A and the phase of A. The absolute value of A, what? Square root of real part square plus imaginary square. The phase, what's the phase? Tan inverse of 6 over 5. You get the phase, the frequency. What's the angle that has this tan inverse? Yes? Which is this? Clear? Are you clear? Can you answer anything now? Now, I found that this is the frequency response, yes? In amplitude and phase. I want now to find the time response. What's the time response? How do you find the time response? If I tell you just the question direct in the exam, how to find the time response from the frequency response? You tell me it's the inverse Fourier transform. This h small of t in time domain is equal to Fourier inverse of h capital of f, the previous one that I found. Yes? It's easy, you just need to transfer this to the time domain, inverse. Then you use the Fourier transform table to be able to find this. You find that this is something like sync, but with different periods and not symmetry. And I can tell you draw it. To draw it, what do? You just take 0, TB, minus TB, 2 TB, and 3 and 4. You find that this is 0 here at TB, at here it's 1, here it's 0, here it's minus 1, here it's 0, here it's 0. What do? You just link these points with each other. You got the curve. If I tell you draw the time response. This is the math you get it from the inverse Fourier transform, and this is the drawing of it. So as you can see, in time domain, the binary, modified binary looks like sinusoidal signal, but it's not really exactly the same because it's not symmetric. It has sync terms somehow, but it's special. And in frequency domain, it has 0 at frequency equals 0. And by this, you solve the problem of DC. Now you can transmit your signal over a wireless channel since you don't have any DC value, and you can not only use it for wire communication, but also for Wi-Fi, LTE, and other communication schemes. So with this, we finish our lecture, and we continue in next lecture where we will discuss and start talking about digital modulation scheme. Thank you very much.